Okay, so I like to go back a little bit to iterate some of the concept and also correct some of the small mistake I made yesterday and in the last example. Okay, we talk about transmission line of finite length. So you see, because this is so fundamental in all RF related subjects. So antennas, circuit, high speed, and so on. So I like to spend a little bit more time on this. Okay, and slow down. So we are talking about finite length. Why we call finite length? Okay, why we call finite length? Okay, you see, because we are interested in the load. Okay, this load can be anything. Okay, can be antenna, can be amplifier, can be a transistor, some of the other logic circuit, and so on, as long as it is high frequency and high speed. Okay, and when we deal with such situation, our observation point or other circuit won't be connected with this load in the infinite far away, right? It's meaningless. So it's always in finite length. So when we call finite length, we always refer to the distance measured from load. Okay, so this is the distance measured from load. Okay, as long as L is finite, okay, then it all fall into this problem. Okay, this problem. So this is why we call finite length, right? Then we said every transmission line electrically, okay, we described by two parameters. One is propagation constant, one is characteristic impedance. And also in the early discussion, we know for different, you see, for open circuit load, okay, you can realize a capacitor. For short circuit load, you can realize inductor, okay, and so on, right? And then also we mentioned impedance repeat every half wavelength long, right, along this transmission line, right? Say if you have at this point, you have the impedance is that. So after half wavelength long, okay, if this is half wavelength long, then if you look at it again, still the same impedance, okay? Same impedance, say if this is 1, this is 1, okay? Same impedance. If you look at this point is 2, so after half wavelength, if looking toward the load, okay, this is 2, right? So repeat, okay. Then this is this property we can, if we divide by current, we define this is impedance at distance L, okay? So that is something for lossless case. Okay, beta is J beta equal to gamma for lossless, right? Okay, so this phenomenon, okay, this property can be easily revealed from this formula. So this formula, how you get this formula? Just V divided by current. Okay, V divided by current. Then from the voltage, we can also represent as this. So what it means is, if we define this is a reflection coefficient at the distance L, okay, looking toward the load. So this is a reflection coefficient. So that means if you have a transmission line, this load at any location, okay, this is our load, right? Then you have a reflection coefficient. This reflection coefficient is the load minus characteristic impedance plus okay, in another word, this load not necessarily has to be here. Okay, it's the end. It depends on where you observe. Okay, when L equal to 0, you can see the load is at the end, right? If the L is a finite value, okay, that is the impedance is that location. Okay, is that location. This is important things. And also, in general, is complex. Okay, but okay, at V minimum, V maximum, CL must be real. Okay, must be real. So you can prove this. You can prove from the expression of this voltage. Okay. Right. So, oh, sorry. This is easily you can prove from here. Okay. Then that's why you see we can take advantage of this, because the real impedance when ZL is real, say RL, right? RL. So this ZL is just load, okay? Load at Z equal to L, Z prime equal to L. Z prime means measure from load, okay? So we have advantage we can take is because it's easy to find this R value from, okay, from standing wave ratio or S, okay? Because standing wave ratio, okay, what's standing wave ratio? Standing wave ratio is voltage maximum over voltage minimum, okay? And also we derive, so we don't repeat this, okay? We derive that equal to the reflection coefficient magnitude, because the magnitude of reflection coefficient down the transmission line at any location, okay, is the same, right? You can prove it is the same. Magnitude is the same, but value is not, okay? So therefore, once we know the reflection coefficient, or once we know standing wave ratio, okay? So once we know standing wave ratio, we have two ways to express this, okay? Or if larger than ZL, okay? Or if smaller than ZL, all right? So that means this, when large means at voltage maximum, okay? Then this is at voltage minimum. Is that clear? Okay, so this is the logic. This is what the logic is. Why we are interested in voltage minimum, voltage maximum is because we can take this advantage. Okay, at the voltage maximum, we can use the standard wave ratio and characteristic impedance. We can easily find the load, which is real. Okay, which is real. Real is easy to deal with than complex, right? Or if this is a minimum, we can find. Okay, we can find. So this is the basic principle we use in our example, right? So in example, we first give a simple case. The simple case is, I know exactly where this load is because my ruler is measured from the load. The second example is my ruler is not measured from the zeros. Okay, let me repeat this again. Okay, because yesterday, you see, at the end, one student asked a question, and I was, I think maybe we still didn't understand the principle. Okay, I encourage our students, we should understand the principle. Don't rigidly remember so-called formula. The formula, if you don't understand, you don't know how to use the formula. Okay, let me repeat this problem again. We have this famous formula. I don't repeat this, right? Okay, this value, suppose is ZL, right? Okay, this is ZL, but this ZL can be anything. This ZL can be this value or can be, you're looking at any location, you can say this is ZL, right? Okay, in this particular example, okay, don't look at this first, okay? Don't look at this first, okay? Then what we have a general equation, okay? We have a general equation is ZL okay, so if I can remember, you can remember, right? So this is not very complicated and also very symmetrical, right? Very symmetrical. This is the general things. Now my question is, if I measured from the terminal, I know this is my reference plan. Okay, reference plan, I know the coordinate measure from 0. Okay, then when z prime equal to this, I got minimum. Okay, then that repeat half wavelength this is minimum again, right? So that means at this point, because this is minimum, the impedance use, okay, here is use Z prime. This must equal to real, and then I use small letter means this is this can be Rm. This is standing wave ratio, right? According to I just discussed, I just reviewed here, right? So at voltage minimum, this load related to standing wave ratio is this, okay? Right? So therefore, I can easily find Rm. Okay, and in most of time, the characteristic impedance is given, right? So I know this. And also at this point is also M, right? But at this point, it doesn't have me, right? It doesn't have me. But then I go the other side, okay? I think this way, this pattern repeat, because same function, right? Psychometric function. So then if it extends toward load, okay, so imaginary, okay, then at this point, this is also M, right? Okay, so this is M, right? Because repeat, okay. Then that means if okay, if I connect, if I connected Rm, say the point A, okay, then I can use this formula, okay, because at this point, what I connect, because at this point I know at least the impedance is known, right? I know this. I can find this distance because this distance plus this, because this must be a half wavelength, because this must be half wavelength, but this is no, right? This is no. All right, so I can find Lm, right? I can find Lm, and the beta is 2 pi lambda, okay? So lambda is no. Then you see, I flexibly use this equation, okay? In this case, L is replaced by Lm, okay? And ZL is replaced by Rm, okay? Don't just rigidly remember this formula without knowing how to use it, okay? I won't give you a question, hey, specifically you substitute in this. This is kindergarten questions, okay? Not our question, right? Okay, we understand this problem, then let's move on. This example is, my ruler is not measured from here, my coordinate. I just arbitrarily put here, okay? I arbitrarily put here. So that's why, you see, because sometimes this location not necessarily Z prime equal to 0, Okay, this question tells you is, okay, when you put a short circuit, that means voltage goes zero. What that happen is, okay, that measured as if the measured put the ruler like this is a ruler, okay? So this is 0.2, right? This is 0.2. So that means so we have a voltage point, okay, that equal to 0. So if you have this, say, this point, I don't know. So I point this is 0.2. This is a 0.42, right? Okay, and so on. So I can easily find this distance equal to 0.4. 0.2, this is 4.2, okay, and so on. So this is a half wavelength is 4, okay, half wavelength is 4. So I know the load, no matter what you put, the load must be, you see, your impedance is a load. After I put a real load, you have 0.2 offset. We have a 0.2 offset, okay? So that means that Z prime is started, okay? Is started at 0.2, okay? This is from this location, okay? We have 0.2, okay? So we have to offset 0.2, right? Okay, then the other question is, when we put the load, then our distance is start from, okay, that the original 0.2 is shifted, okay? It's shifted to, it's no longer the minimum point move to 0.72, okay? So of course, when you place a load, so I don't know what the question is. So if you have a question, you can ask. You can raise your arm, okay, or you can turn on your microphone. All right. So when we place a load, we don't change wavelength, okay, because you don't change a frequency, right? So that means we still have some half wavelengths. So this is a 4.72. This is the second one, right? Okay, this is the second one. Then the question is, if we measure this 0.72, not necessarily the first minimum, okay, not necessary, but however, maybe if we take it as a first minimum, maybe easier to describe, right? So we know this is Rm, okay? So now we know this is also Rm. This is also Rm, right? This is also Rm. So therefore, we know this is half wavelength. Okay, we know half wavelength. But however, this location is not measured from the load. Okay, this point is not. If this is a load, okay, this ruler, we have an offset. Okay, we have an offset from the load. We have an offset from the load, right? So therefore, what we should have is, okay, we measure this Lm first, okay, but this Lm should be offset 0.2 centimeter. Okay, so that means we have 0.72 plus Lm, that equal to half wavelength, which is 4 centimeter. Okay, then, okay, but then this Lm still not a real Lm yet. Okay, because we need to add this 0.2 offset. Okay, so then once you find, if I find this is Lm, so the real Lm is Lm prime plus 0.2 centimeter. Okay, so this is how we find Lm. Once you find Lm, and then we also giving the standing wave ratio. Also, the standing wave ratio is given, so our problem can be solved, right? Okay. So this is what we have. This is what we have discussed. Now let's talk about new concept. I don't have time to repeat the same problem many times. Okay, now we are talking about another 20 points in the final exam. Okay, then from time to time, when we give a load, okay, we said we can find a point that the load is real, right? You see, that point happened at voltage minimum or voltage maximum. So we have we can assume the load is a real number, okay, real load. If this is not a real load, okay, if the load is not real load, is complex load, you can move your reference plane to a voltage maximum or voltage minimum point. Okay, then at that point, the load must be real. Okay, so we don't have problem to find a location down the transmission line that load is real. Okay, but when load is real, why connect a transmission line with different characteristic impedance? Say, if this is a load, okay, I use thicker line indicating this is transmission line, okay? Then if this characteristic impedance is beta 2, then what is a reflection coefficient? Reflection coefficient is, okay, which is not equal to 0. If you don't have, if not equal to 0, if not equal to 0, if not equal to 0, then we have a reflection. If you have a reflection, you have a voltage maximum, voltage minimum, so you have energy being reflected, okay? You have a less efficient, okay, less efficient. So how to make how to make equal to 0. Okay, so this is subject we are going to discuss now, right? Okay, let's see. What I can do is, okay, I connect another piece of transmission line. This transmission line with characteristic impedance is eta 1. Okay, now we have eta 0, eta 1, eta 2, right? So the purpose is I introduce freedom, I can adjust. Okay, let's see, can we adjust the impedance such that reflection coefficient after this inserted the transmission line, the reflection coefficient is 0. Okay, so this is called impedance matching, and specifically is called the quarter wave length, quarter wave transformer impedance matching. It's called transformer. Right? Okay, now let's see how we deal with this. Okay, let's see how we deal with this. Now, I look into load from this reference plane. This reference plane is as this location but toward this side. Okay. Okay, I'm looking at here. Okay, I'm looking at here. Okay, I'm looking at, you see, on the transmission line eta 1 side, I define reference plane. At this time, because at this plane, I couldn't say what lambda 2 or what eta 2 transmission line is. So I cannot say it because I only look it toward the right. Okay, so I don't know what happened on the left. Okay, so at this point, first I can find the impedance. This is what we have done, right? This is what we have done. Okay, we find the impedance. We use the transmission line. We use the transmission line equation. Okay, so I let you to fill in the blank. Okay, now I can find this. Okay, so because here I use tangent function, and the tangent function okay, so I can also write in this way, right? You see, because right now I think this is more convenient for me. In the following discussion, I just write in terms of sine cosine. Okay. This is impedance I'm looking at. Now I found this is reference 1. Okay. Now I found reference plane 2. I found a reference plane 2. From reference plane 2, where I stand is I stand in eta 2. Okay, I stand in eta 2. Right, so not in eta 1 because this is a junction. One is I stand in eta 1. One is this is a reference 1. This is a reference 2. Reference 2, I stand in eta 2. Right? Okay. Now, because you stand in eta 2, you have to use eta 2 standard. Okay. If you stand in eta 1, you use eta 1 as a standard, right? So the first time I calculate this, I use a reference 1. I stand in transmission line eta 1. I use eta 1 as my characteristic impedance. Okay, but when I measure the reflection coefficient when I stand in eta 2, I should use eta 2's characteristic impedance as my standard. Okay, so as my standard, right? Then in this case, I can measure the reflection coefficient, right? I can measure the reflection coefficient. This reflection coefficient is a real reflection coefficient I concern. You see, because I don't like to have reflection in my transmission line, because this will eventually connect to my transmitter. Okay, I use TX as a transmitter. All right, so I need to ensure the energy, the signal generated from transmitter, all conveyed to load. Okay, now I think this is not surprise, right? This is not surprise. We have used this many times, but before we use is they're not necessarily real. Okay, so the load plus reference. Okay, but right now this load is the actual one I observe toward the load at this junction, but however stand in eta 1 transmission. All right. Okay, so this is my reflection coefficient. I need to ensure how to adjust. Okay, how to adjust this new insert transmission line such that reflection is 0. Okay, reflection is 0. Okay, now let's enforce this is 0. Okay, say if this is 0, that means the numerator of this reflection coefficient should be equal to 0, right? So the numerator equal to 0. If the numerator equal to 0, okay, then the numerator, we should substitute this into this, okay, because we expand in terms of sine cosine, okay, we expand in terms of sine cosine. So if you substitute this, set it equal to 0, so that basically we have two things that equal to 0. Okay, we have two things that equal to 0, because one is a real part, you see, because this is a complex number. Okay, this is a complex number. So if this equal to 0, okay, if you don't mind, we spend a little bit more time. So that means eta 1 cosine, say cosine theta, okay? So theta is beta 1 times d, all right, plus j eta 1. This equal to 0, okay? So this means this, okay? This means this. So if this is, because the first part is a real part, second part is imaginary part, right? So if the complex number equal to 0, if complex number equal to 0, this equal to this, and this is this, okay? So if these two numbers equal, that means we have a real part equal to 0, equal, and the imaginary part equal, right? So we have two parts, both both conditions should be satisfied. Okay, so when real part, this is real part, this is a real part. Okay, when real part equal, that means we have this condition, right? Because eta 1 cancel. Okay, because eta 1 cancel, right? And the imaginary part equal to 0. The imaginary part equal to 0 is this equal to 0. Okay, so in this case, to satisfy these two conditions, okay, we have two scenarios. Okay, case 1 is, okay, case 1 is if eta 2 equal to your load, this is load. If eta 2 equal to load and the length of D, okay, this is length of D, is half wavelength or integer number of half wavelengths, because we know wavelengths, half wavelengths, after half wavelengths, impedance repeat, right? Okay, that means, okay, if eta 2 equal to your load, okay, and keep the inserted transmission line half wavelength long, you have no reflection coefficient. Okay. Okay, so this is fine. But however, you see, this is sure regardless what is this? What is characteristic impedance of the inserted transmission line? Okay. So regardless of this, as long as this is half wavelength long. Sure, this is maybe the good thing is if I can do this, if I can do eta 2 equal to eta 0, why I insert a line? That's the question, right? Why insert line? So that means if n equal to 0, this length d equal to 0, I can just, what I tell you is, what it tells you is, oh, you find a transmission line with characteristic impedance same as your load. This doesn't give me any suggestion, right? Okay, because for giving transmission line, the selection for characteristic impedance is very limited. Okay, is very limited. So particularly for those commodity product, okay, transmission line is fixed. Okay, is fixed. Say 50 ohm. 50 ohm characteristic impedance is very popular for cable, for coaxial cable. Okay. Then, however, your load will change. The load will change arbitrarily. Okay, arbitrarily. So this solution is not convenient. Okay, not convenient. Now let's say the second case. I copy this condition back here. It's the same condition. Okay, same condition, right? Okay, same equation I need to satisfy. Okay, but I have another choice. Okay, I have another choice is I let this term equal to 0. Okay, if cosine beta 1d equal to 0, this equation also satisfied. Okay, when this cosine beta 1d equal to 0, that means the d should take you see, take integer number of quarter wavelengths, but not integer number. So that's still quarter wavelengths plus integer number of half wavelengths. Okay, because integer number of half wavelengths repeat impedance. But first of all, you should take the first quarter wavelength long. Okay, in multiple time, We don't need to take a longer one. Okay, we just set n equal to 0. Okay, if n equal to 0, let's forget about this. Okay, that means you can use quarter wavelength long transmission line. Okay, that help you to satisfy the real part conditions. Real part condition. Now let's look at imaginary part. Okay, then for the imaginary part, I can say if this and this equal, because sine beta 1D exists on both sides. Okay, so I didn't eliminate this, you see, because sometimes we need to use it. For example, when we look at the case 1, we use this condition, right? But now let's use the second condition is the impedance for the inserted transmission line. Okay, if you choose its characteristic impedance, it's a square root or geometric average of your load impedance and your transmission line characteristic impedance, for example, 50 ohm. Okay, but define this as a quarter wavelength long. As a quarter wavelength long, you will get a reflection coefficient 0. Okay, so this is very, very useful. If you don't know anything about impedance matching for RF circuit, you should know quarter wavelength transformer. Okay, quarter wavelength transformer. So we summarize quarter wavelength impedance transformer. What you need to do, you insert the line, that line with impedance of this, and its length is quarter wavelength long. Okay, provided your load must be real. Okay, because for complex, at least here, for complex impedance load, quarter wavelength transformer doesn't help. But however, if you find, you say, if you have a load, this is a, say this is transmission line, okay? If this is a complex, okay, if this is complex, then you can find a certain location, the voltage reach to minimum. Okay, then you can find, you can apply your quarter wavelength transformer here, or you can apply the quarter wavelength transformer here. Because at this two location, impedance is real. Okay, impedance is real. It depends on the convenience you choose, the eta 1, right? Because if your load is large, okay, eta 0 is large, this characteristic impedance is large, right? Or if this is small, this is small. So you have two choices, right? You have two choices, which one you should choose. Okay, so that depends on where you connect your other transmission line. Say your other transmission line you can connect to here, right? To here, right? So you need to find then this is eta 1, okay? This is eta 1. If you use Rm, capital M, then you also need to find out, okay? If you put a reference plan here, you need to find out what is Rm, Okay, you need to find out what is RM, right? And this is your oh, sorry. This is your eta 2, right? Then this length is LM. Okay, this is LM. This is your transmission line. Okay. So your RM times this is your eta 1, eta 2, let's say eta 3. So this is eta 3 don't forget you see this, I should say is a wavelength for eta for lambda 2, right? Okay, because this wavelength could be different. It could be different. So is that clear? So this is a way we use for complex load. This is for complex load. Okay. Okay, let's take a break. We resume at 10:30, and during this time you can talk to me. Okay. Any question you can ask me. Okay. What some student wrote a message I couldn't understand. What do you mean? So can you can talk to me. Okay, so let's resume. I received a very good question. Yes, the question is, if the load, complex load, is a pure imaginary. Okay, so if complex load is a pure imaginary, okay, can we still find some location that impedance is real? Answer is no. Okay, it's a very good question. This is extreme case. This extreme case. If hello, hi. Okay. Okay. All right. Okay. 我现在没事，我在上课。好。Okay, I just answered the phone and waiting for the answer. And another question, our student asked, how about the final exam? Okay, so I just consult department office and then to say, do we have further notice? Say, we change the final exam. We changed the final exam to online, and that was originally arranged for face-to-face. But so far, university hasn't gave any notice for change. All right, and maybe say if tomorrow, if university propose to say everyone online exam will change to face-to-face exam will change to online, I will inform everyone, okay? Because we had experience for middle term exam online. It's very, very difficult, okay? And then it's far from fairness, okay, from fair treatment to everybody, and also well, we cannot control, okay. Even we couldn't find the people, and then the video is black, okay. If we have a final exam, this time we must have a very a lot of change on the regulation, and we may need to say you take a responsibility. If we don't see you on the video, you will be out, okay, something like this, okay. Otherwise it's very difficult, okay, for all those online, for those students who are not in Hong Kong, and then we will calibrate your video setting for everyone, okay, to make sure your setting meet our requirement, okay. We will make this arrangement soon, okay. But if every student all take exam online, that makes this job very difficult, okay. Makes this job very difficult, and we don't have that many students just watch, you say, online. If you, sometimes we couldn't see you, we couldn't see your desk, okay, and we don't know what is around you, and then do you think that is fair? So it's not fair, okay. So that is the reason, you see, if any chance we take face-to-face exam, we will take, okay. Okay, that is update about final exam. Okay, and also I think sorry, did I answer that question for purely imaginary load? Okay, so you can look at it from transmission line equation, right? So that impedance. If the load is a pure imaginary, no matter how you move down the transmission line, you never can get a real part. Let me put it this way. You never can get a real part. You see, because impedance, right, is, sure, this is a real, but if the load is imaginary, okay, the second part is also imaginary, right? The second part is also imaginary. You see, this is a GXL, and then you have another G, right? So the denominator is a pure real, and the numerator is a pure imaginary. So of course, this is always imaginary. Okay, so that's why you see we won't let this allow. Okay, if you see, it doesn't make any sense if you have a transmitter, you want to send a signal to some place, but that place is close the door. How you can get in? You have no way to get in. Okay, if this is imaginary part, pure imaginary part, that means you close the door. Okay. Okay, so let's discuss the last concept. Okay, we call resonator. Okay, resonator circuit. The resonator circuit is also very, very popular circuit for RF microwave. Okay, a resonator exists everywhere. Okay, I think two most important concepts. One is transmission line. Second one, in microwave, in RF, will be resonator. Okay, second important things will be resonator. Okay, and then I should say the concept, when you use if you need to use a resonator, that means you are dealing with a more advanced topic than just using transmission line. You understand this? Okay, so that means whenever you need to use a resonator, you are using more advanced topic, okay, than transmission line. Okay, so it's worthwhile to have a basic concept about the resonator, how resonator is constructed from the transmission line point of view. Okay, from transmission line point of view. Now let's say we have two transmission lines, okay, with different phase velocity, characteristic impedance, okay, different, okay, so different. They connect, okay, they have a joint. They have a joint, okay. We call is a junction. Okay, we call this is junction. Okay, by the way, resonator part, I can tell you, resonator part is we don't cover it in final exam. Okay, but you say you can listen to this, or if you don't want to listen, so nothing I can do. Okay, it's as a leisure reading is a very useful concept. Okay. Now let's say we have a junction, okay? We have a junction at this point, okay, at this point. Then we measure the voltage. We measure the voltage. You say, one is measure voltage on transmission line 1, okay? I measure the voltage here. Okay, I measure the voltage here. And also, if I look toward the right, I measure this. Okay, I have two voltage on each side of a junction, right? On each side of the junction. Then, if you have a voltage, you have a current. Okay, so you have a current. You have a current toward right, toward the left. Okay, so we know voltage must be continuous because they measured from almost the same location, right? So voltage is continuous, so we have voltage continuous equation, okay? The current at particular node also should satisfy KCL equation, right? So voltage go out, total voltage go out should be equal to 0. So this is a, so one is the KVL, one is KCL, okay, right? KVL, KCL, right? Okay, now, if we divide, okay, if we divide the second equation, if this is first equation, second equation, if we divide the second equation by first equation, so that means V1, right? And also because V1 equal to V2, so I change this V1 to V2, okay? Right, so we have this equation. What does that mean is we know impedance is defined by voltage divided by current. This is called impedance. Okay, then we also have, we can define admittance is current divided by voltage. Okay, this is called admittance. So, or this equal to 1Z, right? For simple case, okay? For simple one-port device, okay? For one-port device, it is true, okay? It is true. All right, so therefore, this equation is this equation, right? This equation. So Y and Z admittance or impedance, basically the same thing. We have a direction as a reference. Okay, direction is Y1 is looking toward left, Y1. Y2 is looking toward right. Okay, this is because because I call this equal transmission line 1, this equal transmission line 2, right? And in this case, I assume this N is short circuit. Just keep it simple, okay? But if you say, no, I have another more complicated things. This is capacitor. Exactly something, okay? Exactly something. You can connect to anything, okay? I give you freedom. You connect to anything. This is a Z1. You connect Z2, right? You see, because we already discussed how to find Z1, right? For given length, you have arbitrary load. Not big deal, right? Not big deal. Okay. Now let's say we discussed for short circuit transmission line. This is formula to calculate impedance. Do you remember? Do you remember? You see, we talk about the load. The load one beta L is very, very short, okay, tangent beta L equal to beta L, right? Okay, so that means Z equal to J0 times beta L, right? So this equal to J omega L times delta length. If this is a, okay, I put L, right? So that means a very short circuit transmission line equivalent to an inductor, okay, inductor. So we discussed this, okay, so I don't repeat this, right? And then also the beta equal to omega divided by phase velocity, okay. So I use this relation here. Similarly, we can find Y2, okay. Similarly, we can find Y2. All right, so we know Y1, we know Y2, and then condition is if this system have a solution, for Y1 plus Y2 equal to 0, right? Because this is always true. If you have a solution, okay, exists at frequency F0, then F0 is the resonant frequency. I just remove this. It's called resonant frequency. Okay, that means is this frequency at a resonant, but not every frequency at a resonant. Okay, so it has a discrete frequency. Okay, it has a discrete frequency at a resonant, right? So we put a short circuit is just one simplest example. Okay, simplest example. Now we substitute Y1, Y2, okay, into this. We call this equation, we call eigenequation. Or we call characteristic equation. We call this characteristic equation. Okay, equation. So we substitute this into the characteristic equation. Okay, then we call transcendental equation. This become, we call transcendental equation means this is non-linear equation. Non-linear equation means we cannot simply by substitution we can get a closed form solution, right? Okay, but this is still, don't forget this is the simplest case because both ends is short circuit. The two ends may not be a short circuit. Okay, the two ends may be connected by some load, or you may have another section of transmission line and so on, right? So you never know, right? Maybe the other end, maybe the other side is connected with some transistor or IC or something, right? Okay, but this is a way we can set up. What we learn here is we can build up a characteristic equation for a particular problem. Okay, but for different engineering problem, the equation could be different, but the method you can apply. Okay, method you always can apply. Just mean the admittance toward the left, toward the right, all together should be equal to 0. Okay. Then for this particular short circuit, two short circuit transmission lines, we have this equation. This equation we need to find F0, okay? And the F0, okay? Because we have a multiple F0 that satisfies this equation, okay? So we have many F0s, okay? Or you can say F01, F02, infinite number of F0 if you wish to find, okay? Why is infinite number? Because this is a trigonometry function, right? Okay, let's find out. Okay, just give a simple example. We assume the characteristic impedance for transmission line is 60 ohm, and the other one is half of it, 30 ohm, right? Then we have a specific physical length for two, and assume the phase velocity is the same, which is half of the wave speed. Okay, then be careful. You see, I ask you to find 4 lowest resonant frequencies of the system. So this is a system. Okay, so they ask you from lowest one, okay, to find the first 4. Okay, the lowest one to find the first 4. Okay, so that means if we substitute all these no conditions, okay, into this, we have this equation. Okay, and this equation we may need to find numerically. Okay, we may need to find numerically, or in other words, this equation is in this form. Okay, so okay, so for this form, I don't know. You say maybe some programmable calculator can do this. Okay, so I don't know what calculator that can calculate this, but I can tell you the general way. Okay, so if I do this problem is, I define a function. We can define a function f. Okay, f and put capital F. Okay, capital F, which is a function of f. Okay, that if that equal to I define this function. Okay, I define function, then I plot it. Okay, so this is f. This is f. If you plot it, this function must something like if f equal to 0, so f is equal to 0, so that start from 0. Okay, start from 0. But 0 frequency, most of the time we are not interested in, right? Okay, so then this function very likely like this. We continue. Because we need to find the four solutions, right? Four lowest solutions. Okay, the function where looks like this. Okay, in this case, you just find this is f01, this is f02, f03, this is f04. If you like to find, you can find 5. Okay, so once you plot this function, you have many ways you can find it, right? So one way is we call bisectional method, right? So if I can find this and this, okay, if I calculate this function is a positive, this function is a negative, for sure we have 1, 0, right? If you have a 1, 0, then we divide by half. Then I measure this point against this point. I found, oh, this is negative, or this is here. Then I divide by another half. Okay, then this is positive, this is negative, so I can further divide, right? So, but we call bisectional method is very quick. You can search for this and converge very fast, right? And then if you chop this section and this section, both function are negative, then you can assume if this is small enough, this interval is small enough, then you can see there's no solution. Then you further, okay, have another small section. Then you check, oh, these two functions have the opposite sign, then you have a solution, and so on, right? So you find another interval and both functions have the same sign, you don't have a solution, and so on, right? So you can find, okay, using bisectional method, you can solve this. Okay, so this we call how to solve a simple transcendental equation. Okay, this transcendental equation, you don't need to rely on any specific program or calculator. You can write your own program, okay, to do this, right? Okay. Yeah, so far I think you see I finished all the discussion for this class. And suppose I also prepare another 2 lectures to talk about waveguide things. And in the regular teaching hour, you see, because I spend more time to teach more fundamental things. I like to make sure, you see, our students can absorb most useful things. Okay, and if any student interested in next 2 sections about waveguide is I think lesson 30 and lesson 31, and write to TA. Okay, write to TA. We can arrange a time to discuss this. Also, final exam doesn't cover that part. Okay, but it's a very useful part, particularly for nowadays we talk about 5G and then a lot of application using 20 more higher than 20 gigahertz frequency band, and then people use waveguide a lot. Can I see? Okay, the one question. Okay, good. You can ask a question by typing, but sometimes if you can write English clearly, so I can understand better. Okay, then I know what you mean is okay. The question is. Okay, I think the question is, I mentioned I shift the reference plane toward the left, not toward the left, it's toward south. Okay, don't call left and the right. Okay, but you see, because here I call left and the right. This is toward the south. This side is toward the load. Okay, then the question is, sorry, I couldn't understand what your question. Any sign of IM is defined. The imaginary part can be positive or can be negative. I don't need to re-teach circuit theory, right? If you look at inductance, what is impedance? It's a J omega L, right? Then you can say this is JXL. XL is larger than 0. But if you look at the capacitor, okay, what is impedance? It's 1 over J omega C, right? Okay, then you can say minus J XC, right? So XC is larger than 0. So that is negative. Okay, so of course, imaginary part can be positive or negative, but nevertheless, real part must be always positive. Okay, otherwise this transmission line equation is wrong. Okay, so another question is, do we need to move toward the load, the reference plane, in order to find a real impedance? Sometimes artificially, for example, this case, artificially, we extend toward the right, okay? But the purpose is we want to calculate this impedance, okay? This is a trick. This is a trick for us to calculate. But in real application, there's not any meaning we move reference plane beyond the load. Okay, beyond the load, there's no point. But however, toward the source makes sense because we may need to find somewhere, okay, I need to add a matching circuit. I need to add another matching, a quarter wavelength transformer, right? Then that makes sense, right? Okay, so if you want to shift toward the load or shift toward the source, it depends on your application. What do you want to do? Okay, it's not dependent on me. Depend on what you want to do. Okay. So let's we have time. We can talk to the afternoon. Okay. Let's continue the discussion. Oh, okay. So far, I finished discussion of this class. Okay, and this supposedly is the end of our lecture, and very unfortunate, and I have no chance to meet with any one of you, and I don't know if you enjoy this class or you feel painful from this class. Okay, no matter what. Okay, the material we learn as a double E student, it is important. Okay, it is definitely is important part in your career. So unless you are not working in EE related business. Okay. The question is, how do we know if there's no outbreak of? I'm sure university takes a very rigorous means, okay, to ensure that. And then I think is the online, face-to-face exam. If university still provides this solution, and then this solution, I think is trustable. Okay, let me say a few more words about in case, okay? In case if we have to take online exam, okay, then our TA will contact each one of you, okay? We have to set up, we have to regulate your video setup, okay? And then we have to regulate video setup to ensure your setting meet requirement, okay? And then we will take snapshot for the calibrated setting, okay? So in the exam time, okay, if you don't follow that, okay, we will not allow you to take exam, okay? And also in final exam, there's not allowed, okay, if this is take online, okay, not allowed to use any electronics device, okay? So not allowed to use iPad to write your answer, okay? Everybody treat the same, okay? You write on a plain paper, okay? And then this plain paper, we have to examine, okay? The plain paper, right? And then, so that's why you say it's a very difficult. It's a very difficult. So I wish maybe we don't take final exam. So I'm sure everybody happy, right? Are you happy? Not taking final exam? Not happy. Okay. Then we take it final exam. Okay. So okay, say not most of, okay, or most of class take online exam. I don't think so. Okay. So I don't think so. So this university encouraged to take face-to-face, but however, we have option to take online, but you know, online is very difficult to conduct. Do you agree we should take more strict regulation if we have online exam? What is your feedback? So if we don't take a strict exam regulation, we cannot prevent the plagiarism. Okay, the question is, do we have any revision and hint for finding? I think I already gave you enough hint, right? You see, I said, you see, today's discussion is already take 20 marks, and then is this another hint? Okay, in final exam, we don't allow to take any CAT sheet, okay? Not any. And any required formula, equations, we already provided, such as, okay, I can tell you this, such as coordinate transformation, okay? From spherical to cylindrical or to rectangular coordinates, and that is provided. Okay, and then also what else? If we need to use some vector identity, that is provided. Okay, and I don't know how about Tan Xiao, can you check it has the transmission line equation is provided?
Let me see.
Okay, yeah, so that yes or no, okay. I cannot give you the formula sheet on Blackboard because it may give you some hint, okay? But whenever, let me log out the screen share.
The transmission line equation is not provided.
Yeah, right. I don't think I should provide. Maxwell equation is not provided. Okay, for sure. Transmission line equation not provided. I think, okay, the question is if online provide risk for COVID-19, right? And I think anything could be risk. And then if you travel to buy grocery is also risk. And then I think the risk for taking exam is much less than having you see a lunch in a restaurant or go in to a supermarket. Okay, so far I don't know. You say what universities the decision is. Okay, if by tomorrow, if I get information say this face-to-face exam has been canceled, we will make arrangement to each one of the students to regulate the video setting. Do you like? Do you think we should regulate video setting? If you think, type yes. So with Okay, if we don't have a fair regulation, okay, then I will ask university better to cancel the final exam. Okay, so everybody happy, right? Then meaningless. We don't allow to bring any information sheet. Okay, I repeat. This is a closed book exam. Okay, so we finish this class. I will be stay here. So if you like to talk to me, any questions, I'm very happy to talk to you. Okay, so it's the last class, and don't forget send your attendance.